So I keep talking about this thing called the bell-shaped curve. And I probably already slipped up once or twice and called it the normal curve. Now, I'm not exactly sure after all these years why they call the bell-shaped curve the normal distribution. But one of the things I don't like about calling it that is that people assume that the normal curve, the bell-shaped curve, is the only one that's really important. There's a reason that yesterday in the notes I talked about the uniform distribution. There's a reason back in chapter 1 I talked about left skews and right skews. You need to understand that there are lots of distributions that just are out there. But the bell-shaped curve, which again is also called the normal curve, is just one that arises frequently in the study of statistics, so we study it in more detail, okay? But at no time do I want you to fall into the misconception that this is normal versus something else is abnormal. That's not how they use it. In fact, is your book, when they talk about a normal distribution, they capitalize the letter N to remind you that it's not the word normal as in versus abnormal, okay? So I'm going to start again with an example of a uniform distribution just to reinforce the calculations and to reinforce the fact that it is a legit distribution. So in this example, it says past data indicates that a baby's smile lasts anywhere between 0 and 23 seconds, and the probability of any length of time is equally likely. So we're going to sketch and label a uniform distribution. So we are going to be measuring time again along the x-axis, and this is now measured in seconds. And we want to go anywhere from 0 up to 23. And we have a uniform distribution, and then I'm going to drop a perpendicular at the 23, and I form a nice perfect rectangle. Anytime you're studying any sort of probability or statistics distribution, the area underneath the graph and bounded by the x-axis, that area is always equal to 1. To represent 100% of the possibilities. A baby can smile anywhere from 0 to 23 seconds, and the flat line just means it's equally likely. So we know that area of a rectangle is base times height, but because this is a distribution, the area is equal to 1. The base is clearly 23 seconds long, which means the height of my distribution is 1/23. And so now when it says, calculate the probability that a baby's smile lasts between 2 and 18 seconds, I can identify where 2 and 18 are, and I'm just estimating. So this will be 2, this will be 18. And what I'm going to do is drop perpendiculars there. And what I'm going to do then is find the area of that region, which is a subset of the whole region. And setting it up with proper notation, just to really emphasize that, I could say, what's the probability that a baby's smile lasts between 2 and 18 seconds? So the time is in between 2 and 18. So this is how we would write it with probability notation. I think we use some of that notation in Algebra 2. And we could now figure that out by doing the area of this new rectangle. So the area would be the base of this rectangle is only 16 units long. The height is still 1/23. So the probability is 16 out of 23, which if you care 16 out of 23 is about 70%. That's the uniform distribution. Again, I like to start with that one because It's a basic, simple calculation. You're talking about what space is underneath the distribution, and you know that that space for the entire distribution is equal to an area of 1. Well, it's not going to change with a bell-shaped curve. We're still going to talk about the space underneath the curve is going to be equal to 1 or 100%. But it's not as easy to calculate because obviously underneath a bell-shaped curve, it's not a perfect rectangle. You don't have a formula for finding area of a bell-shaped curve. Okay, your geometry teacher didn't teach you about that. All right, so we are going to focus on what's called the normal distribution. The normal curve is what we know as a bell shape. A specific normal curve is described using mean and standard deviation. So what we often do, we write it almost like a function notation. We say the normal distribution has a mean of, and I'm just going to say mu for mean, comma, lowercase sigma for standard deviation. So if someone gave you a distribution and said, oh, I'm going back here looking at these heights. If we knew that it was a normal distribution, we could say it's a normal distribution with a mean of 65.8 and a standard deviation of 5.3. So that's just a notation that we use, okay? The mean and median are both located at the center. And we've talked about that because if you have a nice symmetric curve, whether it's bell-shaped or otherwise, if you have a symmetric curve, your mean and your median should be close to the center together. The standard deviation controls the spread of the normal curve. A larger value for sigma means the distribution is more spread out, okay? So if you know that the area underneath the curve is equal to 1, okay, this area is equal to 1. This area is equal to 1. It just makes sense that if the areas are both equal to 1, if one is wider, then it has to be shorter. If one is skinnier and the area is still 1, then it's going to have to be taller, okay? So area under the curve is always 1. So as standard deviation increases, so as it gets wider, okay, as it gets wider, the height is going to shrink. As it gets skinnier, the height is going to grow, okay? Normal distributions are important because, 1, they actually describe many different data sets. I said they come up a lot. 2, they are good approximations for many probability experiments. And I bolded this one because this is the reason that the authors of your book made this a separate chapter. You are going to be using the concepts we learn here a lot throughout this class, because when we do statistical inference, it's going to come back to a normal distribution calculation. Okay, that's going to happen a lot second semester. And one last time, I'm going to remind you, though many sets of data follow a normal distribution, other ones are still common also, okay? It's not like this is the best one there is. It's just one that we study because it comes up so frequently, okay? So, I think I've mentioned to you before that juniors, when you take calculus next year, or seniors, if you take calculus in college, okay, do you remember studying cubic functions? They might look something like this. You're going to learn in calculus how to pick locations along the x-axis, drop perpendiculars, and you're going to learn how to calculate the area underneath any sort of equation that somebody gives you. It could be a quadratic, a cubic, a trig function. You're going to learn how to calculate that area, okay? So if we have a bell-shaped curve, we should be able to calculate the area under that. Well, wait a second. We just said the area is always equal to 1. But if I randomly gave you two values along the x-axis. How are you going to figure out the area of just part of it, like we just did on that uniform distribution? Well, the good news is there is an equation for the bell-shaped curve. This is it. This is one of my favorite equations in all of mathematics. It has all the good stuff. It has pi, it has sigma, it has mu, and it has my personal favorite, E. It like has everything in it. E, pi, sigma, mu, they're all there. Okay, and what happens is when you think about the bell-shaped curve, how it gets skinnier and then taller, or it gets wider and flatter, because sigma is part of the equation. As sigma gets larger or smaller, that equation ends up being able to be used to define any bell-shaped curve. Now, it takes some heavy-duty calculus to use that equation and do what I'm talking about here. Okay, that is some major calculus. Like, you won't even do that in calculus, okay, in AP Calc. You won't do that. But mathematicians in the past did. They actually used calculus to figure out every little interval along underneath the bell-shaped curve. It's really kind of cool. But since they've already done the work, we don't have to. Isn't that nice? We just have to learn how to take their results and use them. So the first step is what's called the empirical rule. We did this in Algebra 2. And these rules are more generic, okay? These rules just literally count exactly one standard deviation up and down, two standard deviations up and down, and three. Just like what we did on your class height exercise, okay? It only takes into account specifically the standard deviation markers, okay? So using calculus, what mathematicians figured out is if you have your mean dead center, if you count back and forward one standard deviation, you will have about 68% of your data in that region. Okay, so 0.68. If you go out a step further, now you'll have 95%, 0.95. And if you go out a step further, you'll have 99.7, 0.997. Now I'll tell you what, in actual data collection, that number very often hits 100%, okay? Because this is a very theoretical model. And remember, theoretically, I mentioned yesterday, the tails never touch the x-axis, okay, theoretically. What we also did in Algebra 2 that you might not remember is we broke it down further. I'm going to split this guy right down the middle. So if there are 68% of the data in that center piece, how much is on each side of that line that I just drew in? Not a trick question. 34. Okay, I'm going to mark that. So we would have 34% on each side. Yep. Okay, so now if you go up to the next boundary line from here to here, that gives me 95%. But if I already figured out the 68% in the middle, what I'm going to do is take that 95%, lose the 68 that I've already dealt with, and it means this piece that kind of looks like a trapezoid and this piece that kind of looks like a trapezoid, that's 27% together, which means each side is going to be 13.5. Do these numbers at all look familiar from last year, or is this all long gone from your brains? All right, go out one more step. 99.7. But we already learned about the 95, so let's get rid of it. And so what's left is between that triangle looking piece and that triangle looking piece together is 4.7%. So each piece is 2.35%. And then if we figure, if you zoom in, you can see there are little tails there. There's an itty bitty little triangle looking piece there and an itty bitty one there. I'm going to take 100% and I'm going to lose the 99.7, 0.3 between the two itty bitty triangles together, which means each itty bitty triangle is 0.15%. Now be careful on that. 0.15%. If I went through and changed all these into decimals, this would be 0.34. This would be 0.135. This would be 0.0235. And this one would be 0.0015. It is super, super tiny. Because basically, if you have a distribution that fits a bell-shaped curve, a normal distribution, your chances of being more than 3 standard deviations away from the center is only 0.15%. Okay, your chance of being this low or this high, very slim. And that goes back to, remember the example about Babe Ruth? And his Z-score was 5 point something. Okay, your chance of being just beyond the 3 is only 0.15%. Babe Ruth was at a Z-score of over 5. Okay, the probability of having a performance like what he had, okay, next to nothing. Be sure that you do not apply any normal distribution rules to a non-normal distribution. Okay, this rule only fits with a bell-shaped curve. But if you do have a bell-shaped curve, now we can do some calculations. And again, this should be a review from what we did in Algebra 2. The mean batting average for the 432 players in Major League Baseball was .261 back in 2009. All right, so that is the mean. That goes dead center, .261. The standard deviation was 0.034. So the first thing you would have to do is you would have to take the mean and you'd have to add a standard deviation. And I did that. So it's 0.295. Then you have to add a second standard deviation, 0.329. And then you add a third standard deviation, and I have 0.363. Now I'm going to emphasize, we only do 3 of them because calculus and the empirical rule have told us that the chance of being beyond that is probably not going to happen. So we don't even bother labeling it. But then we go back in the other direction and we start subtracting 0.034. So this would now be down to 227, 193, and 159. Now, it doesn't mean that there was not a baseball player that year who maybe batted a 140. It doesn't mean that. But the probability of that happening was pretty tiny. Okay? Most likely, the majority of batters batted between a 159 and a 363 that year. But now what we can do is we could say what percent of batting averages were above 329. All right, so just to emphasize notation, I'm going to do this again. Percentage of batting averages that were above a 329. So we can come up here and we could look at this and say, okay, the 329 was marked at 2 standard deviations. But we want to go above that. So you would then go back to your empirical rule and say, okay, if I'm at 2 standard deviations, I need to go anything above that. I would have to take the 2.35 and the 0.15, those 2% get added together. So there's a 2.5% chance, 0.025 is your probability, that if you randomly picked a baseball player from the list of 432 players that year, there is a 2.5% chance that you're going to pick somebody who batted higher than 329. What percent of batting averages are between 193 and 295? All right, so I go back and look at my chart again. Here's 193. That's 2 standard deviations down. And here's 295. That is 1 standard deviation above the mean. So we need to know the probability or percent of being in that region. 2 below, all the way up to 1 above. 2 below, all the way up to 1 above. So you would have to take the 68% here and now add the 13.5. So really you could think of it like this. You would be talking about 81.5% or 0.815. So again, if you were to randomly pick one baseball player from the 432 players that year, there's almost an 82% chance that that person would have batted between a 193 and a 295. That's not so bad, is it? Okay, so you need to understand these are all estimated values. Okay, these are all estimated. There is a way to get more specific. And we're going to learn how to do that. So the set of z-scores are called standardized scores because they apply a neutral scale with no units. And I think I've talked about that already. It allows us to compare different data sets. A standardized normal distribution will always be labeled like this. And so the label would be, it's a normal distribution centered at 0 with a standard deviation of 1. That is a standardized normal distribution right there. Huge caution. You can standardize any data set you want. You could take a skewed distribution and you could standardize it, okay? You could do the z equals x minus mean divided by the standard deviation. You can do that to any data set you want, but it doesn't make the data set become normal. If you have a skewed distribution to begin with, if you convert to a new scale, it's still going to be a skewed distribution. It would be like converting feet into inches or inches to feet. You can change the label all you want, but it doesn't change the distribution, okay? So now let's get more specific. If z-scores are not exactly 1, 2, or 3 standard deviations away, then the empirical rule doesn't help us. Okay, so for example, back to your heights exercise, okay, we estimated that this person had a z-score of negative 0.33. We estimated. We didn't know for sure. Well, now we know how to calculate it, and what we can do then is we can actually figure out a better answer for the area. All right, z-score table. Now this is in, remember I gave you a formula packet at the very beginning? Okay, this is in the formula packet. So this is just a duplicate of what you already have, but I'm giving you just a page of what we call the z-score table. There's 3 there. I'm trying to find, these got copied. The copier is being really stupid, so I'm trying to find all the good copies. I guess 4,000 is all the bad copies. So here's 2 good copies, 1 2 nights behind. There's 2, and here's a 3rd good copy. Okay. None of our copiers are working well right now. One of them keeps jamming, and the other one is feeding all the pages crooked like this. Great. Great. Okay, yeah, these are bad. All right, I'll use a bad one. So z-scores. I had mentioned the other day that when you calculate a z-score, we round to 2 decimal places. And I said there was a reason for that. And the reason is just because when someone made this table years ago, they set it up so that everything was measured to 2 decimal places on the outside of the chart. Okay, that's the only reason we go to 2 decimal places, because people have done it for decades. The z-score table will stop at about positive and negative 3.4. And if you read down the column, you can see there's a positive 3.4 on one side and there's a negative 3.4 on the other side. The chart stops there because we know that going beyond even 3.0 rarely happens. So they went up to 3.4. Okay, so they're like, that's enough. We're going to stop. It can be found at the back of your book. It's also in the formula packet that I gave you, and I will provide it to you in that formula packet that I will give you on test days, and you'll have those same formulas for the AP exam. I will caution you, if you are just Googling z-score table, there are different versions of the table out there. They all give the same numbers, but you read them a little differently. So if you're ever on a different one that's laid out differently, be really careful. Okay, so the one I gave you has a front side that has positive z's and it has negative z's. There are some tables out there don't give positives and negatives, because what it does is it assumes that you understand that the bell-shaped curve is perfectly symmetric. So whatever happens over here has a twin over here. Okay, so different tables read differently. I just recommend to people stick with ours so you don't confuse yourself. Okay, so on these problems, I'm giving you the z values. We don't have to use the z formula. I just want to teach you how to read the table. I also said consider making a sketch. All right, so on each of these, it tells us to assume a standard normal distribution. So on each of these, I'm going to draw me a bell-shaped curve. All right, x-axis, 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 whatever. Doesn't have to be perfect. All right, if we have a standard normal distribution, 0 is always dead center. 0 is dead center. Basically, you got to picture this diagram right here. So we want a z-score of negative 0.92. Now, you don't have to be ultra precise. For me, I look at this and say, okay, negative means I'm on the left side of 0, right there. I don't even worry about, am I too close or too far from the mean? Doesn't matter. And I draw my perpendicular. And I want to be less than that. So I'm going to shade everything on the left. Okay, so got your table ready? We have a negative z value, so go to the negative side. And what we have is negative 0.9. So you want to be on this row right here. Can everyone find that? Negative 0.9. Now, where does the 2 come from? That's that number up there. Because we want the 2 to be in the hundredth spot. So I'm going to take this column and this row, and my answer is 0.1788. So if someone said, what is the probability that z is less than negative 0.92? My answer is 17.88%. That's not so bad, is it? Now what you have to remember though is, look at the diagram that's at the top of the chart. They are showing you, 0 is dead center, so here's 0. They're saying if you have a negative z-score, we're giving you the answer that is shaded over here. And that's exactly, that matched our picture. That matched our picture. All right, let's look at the next one. Negative 2.79. Okay, so negative z-score means I got to be on the left, almost negative 3, so I'm pretty far to the left even. But I want to be greater than that. So greater than means all of this. Now, do you see that doesn't match the diagram on the chart? Because the diagram says if you have a negative z-score, this is telling you all the answers are going to show you what's on the left side. So when you read your chart, it's actually going to give you this right here. The chart is going to give you that answer. All right, let's find it. So find negative 2.7 in the column right there. There's negative 2.7, and we need 2.79, and that means go all the way to the end, 0.0026. But that doesn't answer the real question. How do we get the real answer? Okay. Now, yeah, 100 or 1. Okay, if you were using the decimals, think of subtracting from 1. If in your mind you like to convert to percents, then subtract from 100. But yes, to get the answer we want, the probability that z is greater than negative 2.79 is going to be 1 minus 0.0026. So our answer is going to be 0.9974. And that kind of matches the diagram, because don't I have almost the whole thing shaded? Then my answer should be almost 100%. All right, then the last one on this page. This time I have a positive 1.75. So positive, go to the right side and drop your perpendicular. And we want to go greater than that. All right, so it's a positive z-score. So flip the table over to the positive side. Find 1.7 down the first column. There's 1.7. And we want 1.75, so find 0.05 here. And that answer says 0.9599. Does it look like I shaded almost 96%? No. Not even close. Because once again, if you look at the diagram, this is telling you that no matter what z-score you use, the table will always shade in left. I always tell people, you don't have to really memorize that too much. If you make a sketch and you color it in and you look at this answer, you're like, okay, no, that's small, that's big. I got to subtract from 1 again. The probability that z is greater than 1.75 is going to be 1 minus 0.9599, which will be 0.0401.
So instead of switching back and forth, like doing the 1 minus, like whatever it is, the negative side.
All right, and this is why some z-score tables don't have a positive and a negative sign. Because yes, because of the symmetry, I could have looked up z less than negative 1.75. If I had just stuck to the negative side, there's negative 1.75 right there, 0.0401. You can get the same answer if you understand that there's symmetry involved, okay? For me, that's how I used to do it. I actually do this more now. For some, I just draw the picture and it just helps me think it through, okay? All right, so honestly, I would recommend, if you want to do any homework, just the 41 through 45 right now. We did not get far enough through using the table, because now what we're going to learn how to do is read the table backwards. And I said, I have section 2 on the calendar for a couple of days. There's a lot of information. This data set right here, it's a big data set on the next page. We are going to need that data set in our calculator either tomorrow or Thursday. Now, a lot of you physics, like the other day, someone said they had to wipe out their data because they had done something in physics. I get that. So if there's a way for you to, especially Inspires, how you can save documents and things like that, enter that ahead of time and just save it. You guys know how to do that in your Inspires?